Yeah. So, one thing I forgot to mention last time when I did the schedule up on Fonto was that you are going to have one submission. Runal mentioned it just briefly. You're going to have one submission, but you're not going to get the assignment for the submission until we start part 3. So for now on the schedule, it is put up as week 39 on the Thursday in week 39. But if we fall behind the schedule or something like that, I'm going to postpone it until we start part 3. Because it's in part 3 and part 4 where we get just a little bit of maths to do, a little bit of physics to calculate with regards to diving and gases and stuff. So that's going to be a part of the submission. That's why I'm waiting until we start that stuff before you get the assignments. And then the deadline is in week 45. If the release is postponed for 1 week or more, I'm also going to postpone the deadline so that we will still get the correct amount of weeks for your submission. Yeah, we were talking about lighting and stuff for visibility and everything. Just have to. So we mentioned the 3 main equipment stuff that they use to help them with seeing stuff when they're underwater. So it also means that not only are the pilots of the ROVs, not only are they looking at a TV screen where they see the video feed from the ROV, but they are also looking at a whole host of other screens that are telling them like the distances to the stuff around them and everything. So they have quite a lot to look at when they're working. So they got to keep in focus when they're working. So another design premise we have to take into account when we are designing stuff for subsea use is marine growth and bacterial activity. Because I'm pretty sure that most of you have seen algae growths and stuff in water. It will, if you submerge something in water and you let it stay there, even if it's clean, fresh water, it will, after a while, it will get sort of slimy. And that's just bacterial growth from the water. Because there will always be bacteria in the water, and it will sort of stick to the surface, and it will find something to eat, and it will just replicate and can become quite the problem, especially the marine growth, which is when you are above a certain depth, when you are between the surface and a certain depth. You get a lot of marine growth, which is sort of the grassy greenery stuff that you get growing underwater. And that can actually that can start clogging up machinery and everything. So it's nice to know that you have taken it into account when you're designing. And the same can happen with bacterial activity. You can get really thick layers of bacterial activity, so you can start just blocking movements on the machinery and everything. So it's the nice thing about the marine growth, at least, is that if you get deep enough, there won't be anything alive because it won't be getting any daylight to get any do any photosynthesis and stuff. So when you get deep enough, you sort of eliminate this one. But the bacterial activity can still happen on pretty deep stuff, mostly because of like these sulfur volcano stuff I was talking about. There's a lot of bacterial activity around those, and it's just amazing how they can live under those conditions. It's pretty cool, actually. So here's a nice little clip, because not only do you have the stuff that's growing there, but you also have the larger stuff that's living in the sea. there's an ROV, and you can actually see here, it's a nice thing to get to see because here you have ocean currents that are pulling on the ROV and stuff, so it can be really difficult. It looks fairly uncomplicated to move this robotic arm and have it grapple something, but when you're constantly being shoved around by ocean currents and stuff, it's really not that easy to grab a hold of something. So what he's doing here is sort of trying to release this shackle, so he's trying to get this wire, so there he managed to pull it. So he released this huge lifting wire, and then when he gets back here, then suddenly you have a huge sperm whale. It's been listening to all of these sounds that the ROV has been making, and it's curious, so it's just showed up and wondering, what's going on here? This can be a huge problem. As you can see, the umbilical for the ROV, it's sort of pushing up against it and everything, and you can actually risk it starting to pull stuff with the ROV. So it can be, especially with whales that are that big, it can be a real problem. When you get schools of fishes, it's not that big a problem with them getting in the way of stuff, but it's more like visibility. If you get a whole huge school of fish that come in around because they are attracted to the lighting on the ROV, they want to be where the light is, so they can just come in front of the cameras and then you can't see anything. So that's one of the things that they have to deal with on a regular basis when they're working subsea. Let's see if it's can. So another thing we have to take into account is the ocean currents. As you saw with the ROV, it's quite difficult to maneuver and stuff, which means that the ROV has to have specific requirements to its thrusters. They have to be powerful enough to sort of overcome the ocean currents and gain control over the vehicle. But still, ocean currents will be a problem because they will be changing direction just like the wind does up here. It will slowly be changing direction and stuff, and suddenly it's been counteracting, the pilot has been counteracting the ocean current coming from this side, but then suddenly it's coming from that side and he's moving backwards instead. So it's a constant battle to get it to work correctly. But still, for our part as designers, we have to realize that this is a problem, so we have to make the equipment strong enough, or powerful enough rather, to combat these effects. And there is a relationship here between the drag forces on the ROV. But probably you've seen on the television or something when they're testing new cars and stuff, they put them in a wind tunnel where they have a lot of smoke being blown across the car just to see how is it moving as it moves across the car. That is to see the drag effects, because you get all types of cars were fairly sharp edges, so the smoke would get sort of turbulent when it's moved across the car. So newer cars, they are more rounded in their shapes, just to allow it to the air to move more easily across. You get the same problem in water. The water also has to move across the ROV, or under it, or beside it, or anything. And water is a lot more thicker and heavier than air, so the drag effect is a lot higher in water. You'll see the same thing if you're in a pool and you start moving your hand in the water. You will feel that there's a lot of resistance there when you're moving your hand. So the ROVs will be battling with the same kind of resistance. Only a work ROV can easily be the size of this table here, maybe even higher and even wider. So they can be really huge. They often weigh a ton or two. So they will get a lot of drag from the water. And the more drag they get, the larger they are, the more drag they experience, and the more powerful thrusters they have to have in order to be able to maintain control. And we also have large distances. Not only is it far out to sea, often. It's a long distance from land, so you basically have to bring along everything you think you might possibly need. Either that or you'll have to wait for stuff to be shipped to you. But also there's quite a lot of distance between the surface and the ocean floor when you are going to control stuff. So the equipment has to be safe and reliable, even though it has huge distances to operate across. We'll be getting into that more in the first appendix in part 2, because that's more about the subsea production systems. So we'll see more how do they keep control of everything that's being produced down at the ocean floor. Also, like for the ROVs, they have an umbilical where they get everything they need of electricity and signals come through this umbilical. But basically, it's just a very thick cable that's running from the ship and down to the ROV. And when this cable has to be very long, you also have to boost the voltage in order to manage to get the same effect across it. Because you remember from the thermodynamics, we were talking about the effect of power plants. We calculated it for some of them. And the effect, the P, that we were calculating, also goes from one end of the cable to another. You have to try to get the correct amount of effect to the end of the cable. But you get some sort of resistance in the cable, electrical resistance through the entire cable. And the longer the cable is, the more resistance you will have. So by boosting the voltage, the volts, if you boost those, you will maintain the effect. Because you have this trifecta. I'm really rusty on my electronics, so I'm not quite sure if I'm doing this one correctly now, but it's probably, I'm probably putting my values in the incorrect places here. But you have a trifecta between the voltage, the amps, and the ohms, which is the resistance. But if you increase the resistance, you also have to increase the voltage in order to keep the amps at the same level. And you use the amps when you're calculating the effect. So that's why you have to take this into account with long cables and everything. Yeah, also you have the signals going through the umbilicals, which also have to travel a great distance. And up until fairly recently, most signals were transferred by use of electrical cables. So they were just sort of sending pulses through the cables to tell the equipment what to do. Now, basically all of newer ROVs that are being built, they are using Ethernet cables. So they're basically using fiber optics to transfer the signals instead. Not only is it more reliable, but it's also faster to transfer. Because when you bundle together a lot of wires in a cable, so maybe you would have the main wire going through with the power delivering the effect, but you would also have the signal wires bundled into this thick cable. The problem is that when you send electricity through any of these, they will generate magnetic fields. And since they are so close to each other, those magnetic fields will affect each other. So the magnetic field from this one will affect all of those around, and the magnetic field from this one might affect this one, and that one. So that you sort of get what they are called basically interference or noise. So sometimes the signals that you were sending down would have so much noise coming in from the other wires inside the umbilical cable. It would have so much noise in it that the ROV just couldn't handle it. It would just say, well, what? I don't understand what you're telling me to do. So it would be completely impossible for the ROV to execute any maneuvers because it wasn't getting the correct commands. But with the fiber optics, you have replaced these other wires with the fiber optics cables, and they use light instead of electricity, so you don't get the noise problem. So that's a huge improvement with the reliability of the signals when you're sending those through. And the problem is that, especially when you are getting noise and stuff, and the ROV might not be responding as you had expected it to do because it simply didn't understand the commands it was being given. Suddenly you could have it doing something it wasn't supposed to do. Maybe it unscrewed something too far, or maybe it tightened it too much so that it actually broke it, or maybe it actually crashed into something because it didn't react when you told the thrusters to stop. And the problem there was that the worst case scenario was, of course, that you would have a leak, that you would start leaking oil or gas into the ocean. And that would be a heavy maintenance job to fix this, because it would be all hands on deck. We have to do this as quickly as possible. You would have to get in other ships that were in the area that could help, and everything would have to be tried to do it as quickly as possible because you want to avoid a catastrophe in the environment. So that's it could potentially also become life-threatening, especially if you are using a combination of ROVs and divers down there. So you actually have a human being down there with this diver and with this ROV that's doing something that you're not quite sure what it's doing. It might ram the diver or anything. You don't really know what's happening. So it could potentially become life-threatening for divers also. So getting this reliability up by using fiber optics, that's been a huge achievement. Also, whenever something would go wrong, and it still goes wrong every now and then when they're doing subsea operations, and they might have to get a bigger vessel in to do the repair jobs, because there are different sizes to the vessels, and the smaller vessels are often doing the sort of easy work, inspections and just checking out stuff, and maybe just turning a few valves or something. So if something actually goes wrong, they have to get a larger vessel in, because the larger vessel has the right tools for the job to fix what's gone wrong. And that's very expensive. We'll get into it in part 5, I think it is, which are the vessels. We'll be looking a bit at the day costs and stuff, and I'm not kidding when I'm saying hundreds of thousands of Norwegian kroners a day for those vessels. So that's very expensive. So you're talking about many tens of thousands of dollars every day it's out there working. And the larger the vessel is, the more expensive it becomes. So it's a huge problem when things go wrong there, because it gets so extremely expensive so fast. You also have the weather and waves. Usually you have a surface vessel which is controlling the operation, and the surface vessel is up top. It's being exposed to the weather, winds and waves and everything, and it's usually connected to whatever is subsea through cables and lifting wires and everything, which means that you will constantly have, if your surface vessel is moving like this constantly with the waves, something is going to happen with the wire that's going down. So you will have constant motion in the wire. That can also be a problem for the ROV, because the wire will often go down to the ROV, and if you're constantly tugging and pulling on it because you have that much waves, the ROV will have huge problems doing its work. Not only that, but you also have to lower everything from the ship into the sea. And the worse the weather is, the more difficult that is going to be. And usually you get what they call weather windows. So they basically say that, well, if we have waves of more than 4 meters of significant wave height, we'll get into that later, what the significant wave height is. But the significant wave height is a way of measuring the height of the waves. And often it is 3.5, 4 meters. Maybe if it's not a critical operation, you might have 5 or 6 meters. But often out in the North Sea outside of Norway, you have 6, 7, 8, 9, 10, 12 meters. So it's pretty difficult to sort of get the correct weather for your operations. Which again means that the vessel, which is costing this huge amount of money every day, might be out there for several days just waiting for the weather to get good enough so that they can do their operation. Which is also why most of the operations are being done during the summer, because that's when we have the nicest weather. So it's easier, less waiting time for them. So often they do the preparation work during the winter half of the year. So they prep everything, make everything ready, and then come April, May, they start putting stuff onto their vessels and sending them out to do work all summer. And then it's really chop all the way through the summer. So they often have very busy summers, when like Deep Ocean here, who are running a lot of vessels. They often have very busy summers. Not only the guys that are working on the vessels have busy summers, but also the engineers, because there is always something unexpected that shows up. So the engineers here on land often have to try to figure out stuff for the guys out on the vessels. The guys on the vessel notice something. Whoa, this wasn't supposed to happen. And then the engineers here have to try to figure out, oh, why did it happen, and what can we do to make it better. So it's I know that they often do some overtime during the summer, which is even worse, because some of them are always on vacation. Since it's summer, they want to do vacations with their families and stuff, and then it's even more overtime for the guys that are still at work. So it can be very hectic for those guys. And of course the waves here up top, you might think that they would reach pretty far down, but they only reach maybe 10 meters or so down. That's the only area where you actually get much effect from the waves, where the ROV itself, if it's less than 10 meters from the surface vessel, it will actually be affected by the waves itself. When it gets further down, so 100, 200 meters, it's only the cable and the fact that it's fastened to the surface vessel. That's the only thing that's being affected by the waves directly. But still, you will get tension in the cable and stuff. So some of the ways that they actually fix this for ROVs is that they do create a sort of a garage for the ROV. So they basically have a box which is fairly heavy. The ROV has a lot of buoyancy elements in it, which makes it more or less neutral in water, so that maybe some of them are even positive buoyancy, so that they would, if you shut off their thrusters and everything, they would actually rise to the surface very slowly, but they would still rise. So that is also like I talked about with the poor visibility and the sediments, that they are, if they turn the thrusters downwards, they will swirl up a lot of sediments and create a fog that they can see through. That's also one of the ways they counteract this, is by making it so that in order to maintain their depth, they actually have to point their thrusters upwards, just to push the ROV down. So that's a way to avoid the sediments and everything. But the TMS, as it's often called, is not buoyant in the water, so it's heavy, so it's just hanging there in the lifting wire. And then it has a spool for the umbilical, so it just spools out the ROV, and then you will get all of the wave effects will go from the surface vessel through the cable into the TMS. But then this part, the small umbilical that is going from the TMS and out to the ROV, that's just floating there in the water. So it's not a problem. Like you saw on the clip with the umbilical that the whale was sort of nudging and scraping against. It was just floating there in the water. So it's not affected by the waves at all, because this one is more or less just sat there. It just sits there hanging on the cable. So it has a little bit of movement, but not much. So that's the way they avoid having this problem with the ROVs. But then again, that works for a working ROV, an ROV that is supposed to go down to a certain area and it's supposed to stay there and do a lot of work. If you have an ROV that's supposed to follow a pipeline along the seafloor, then you can't have the TMS there, because then it will have to drag this one with it. And then you get a lot of drag forces on that one as well as on the ROV, and then the ROV has to have super powerful thrusters in order to do this. So usually if it's an ROV that's going to do survey work, as it's called, which basically means that it's going to check along a pipeline, and the pipelines, they are kilometers after kilometers after kilometers, several thousand kilometers of pipelines that they just have to cruise along up top, and they just look at it, and they have a lot of sensors which tell them a lot of stuff about the pipeline. And then it's often best if they can go as fast as possible. So they don't want this huge weight to pull. So the last part of part one is prospects for the future. And I don't think I have any notes on that one, no? So the driving force for the subsea technology has of course been the oil and gas field, because they need it. And that's specifically true for Norway, but it's also very true globally, because all oil and gas that's being done offshore, it needs subsea technology. Especially since it's becoming increasingly deeper waters that they're working on. It started off outside of Norway, outside of Bergen, actually, with the Troll field, which was about 350 meters deep. And then they decided to do, well, many platforms are just a lot of pipes that are put together to sort of keep the platform up top, and it's on the seafloor. But the Troll, it was so deep that they decided, well, we'll have to do it with concrete. We need something that's stronger than just this. This one is, when it gets too long, it's liable to just break with the waves. So what they did was actually a lot deeper, and then they created huge pylons in concrete going up to the platform. So you have 350 meters or so, even more, because it has to go above the surface. So you have more than 350 meters of concrete, and it's really huge and heavy. Actually, I can see if I can find a picture of it. Let's see. Yeah, there you have a comparison picture. Several skyrise buildings. One in Malaysia, but the Petroleum Towers. So it's actually larger than that one. So if you go up to the top of the torch, you are well above 450 meters. And this was something they built on land, and then they moved it offshore and put it down. So that's pretty amazing. So you can actually see these pictures where they are floating it. That was a good picture. So they fill these concrete pylons, they fill them with air just to make them buoyant in the water, so that it will float higher. And then you can see as they get out into deeper seas, here it is when they put it in place. So you can see it's sitting further down in the water when it's been placed there. And you can actually see, I've worked a bit at the Statoil plant outside of Bergen, which is called Kolsnes, and that's all the way out in on the coastline outside of Bergen. And then you can actually see every night, if you stand there and just look out to sea, you can just barely see the torch. So when they're burning gas, when they have excess gas and they have to burn it on the platform, then you can actually see the flame when you're standing on Kolsnes there. So that's pretty cool. And but that was just 350 meters. We've gone way further since that. So outside of Brazil, I think they're down to well over 3,000 meters depth. I think they're at 3,500 or something for the deepest there. So they are constantly pushing it further and further. And in Norway, this means that divers, they are completely out of the picture. We had earlier, divers were allowed to work down to 300 meters. But then I'm not sure if you've heard about it, but we had this accident that happened. They were testing something down at 3,300 meters in one of the fjords here in the area, actually. I think it was in Ølen, where Westcom have their facilities. So it was in one of those fjords, which is really deep. So they put out at 300 meters depth. They made a habitat for divers and everything, and they were going to test well a pipeline. Because the whole point with continuing to do work outside of Norway was that we have a 300 meter deep trench going along the entire country, which meant that the pipelines had to be put through this trench. They had to basically go the trench more or less like this. You have land up here. The pipeline would have to follow the trench and then up to land. So that's they had to be sure that if something went wrong with the pipeline, if we had a break in the pipeline down at the bottom there, they had to be able to fix it. So at 300 meters depth, they had to do welding tests with divers just to see this. And there was actually a fatal accident when they were doing these tests. So one of the American divers that were in the experiment, he ended up dead. And there's been a lot of investigations into all of this and a lot of documentaries and stuff. And I think the last documentary I saw, there was something about something went wrong up top in the surface vessel, and he didn't get his breathing gas sent down to him properly. So he ended up passing out, and then by the time they realized that he had passed out, it was basically too late. So they managed to get him up, but he didn't survive. So in Norway, they ended up creating a limit at 180 meters. So professional divers in Norway, they are not allowed to work at greater depths than 180 meters, which means that everything below that has to be done by ROVs. So outside of Brazil, where they're doing all of this stuff at 3,000 meters, they are using only ROVs. But I do know that they have had divers down to 400 meters outside of Brazil, and they do so on a fairly regular basis. So that they are still using divers fairly deep. So it's I think it's just a bit about how much of a safety aspect do they have. So Norway is very conservative when it comes to safety in the workplace. So we would, I think the authorities in Norway, they would love it if there were never any fatal accidents in the workplace. That would have been the best. Of course, that would have been the best for everyone, workers and all, but many other places in the world, they don't have that ambition of having zero fatalities. They have it on paper, but they don't really do everything they can to avoid it. So, yeah, so the ROV technology has meant that we can also go deeper outside of Norway, and just like Brazil. I think the deepest field is around 1,000 meters. We'll get into it later on. So we'll start on part 2. And I'll be posting these presentations, I'll be posting those on Fonto as we finish each part and each appendix. So I create a presentation for each part and appendix, because if I don't get all the way through it, I will continue in the next lecture, so that when we have gotten all the way through it, it will be posted onto Fonto. But I will only be posting this one, because apart from that one, I'm only using the same compendium as you are doing for my notes, so there's not really much more to show. So we're going to get an introduction to subsea production systems and the relevant standards that are used in the industry. So we've already talked about increasing depths that we are. Yeah, we'll do a break before we continue. Actually, that was a good one, John. Then we're back. Yeah, we had increasing depths. We have already talked about that a bit, that we have to go deeper and deeper to find more oil reservoirs. And also, the oil prices have been, well, the last 2 years they have been dropping, still dead, but before that, the oil prices were generally becoming lower and lower compared to the cost of extracting the oil. So that you were getting less per barrel of oil that you extracted, but you were still making enough money to actually do this stuff. That's been a problem for the last 2 years because Statoil and the others have basically been having a hard time actually making money, or at least making their budgets for new developments work with the current oil prices, which is around $40 a barrel or something. 2.5, 3 years ago, we were up at almost $120 a barrel, so it's just a third of what it used to be. So I can understand that they are having troubles with seeing how their budgets would actually work, if they would actually make money if they are developing a new oil field, or if they just have to put it on hold for a while. So that is one of the reasons why the Norwegian industry has had a bit of a crisis for the last few years. One of the reasons why I'm working here and not at Imenco anymore. So there's a lot of things that has to be taken into consideration when they are developing new stuff. But we are constantly getting new technologies also, which make things easier, more reliable. It gets simpler. It might not exactly become cheaper to build or produce, but in the overall run, when you are making it work for 5, 10, 20, 25 years out in an oil field, then you will see the benefits of this new technology. It's much like the switch that EU has now done, that for the light bulbs, we are no longer allowed to use the old kind of incandescent light bulbs. We have to use the halogen or LED light bulbs, which is sort of to my old grandfather. He thought this really sucked because the LED light bulbs, they are about 10 times as costly as the old incandescent ones. But the thing is, you get 20 times more lifetime out of a LED light bulb. So it doesn't really matter that it matters right there and then when you have to use the money to replace your light bulb, and it's 10 times more expensive than what you thought it was going to be. But in the long run, it's going to take twice the time before you have to replace it, at least. Or 20 times, 20 times the time before you have to replace it, so that it will last for ages. So you get twice the value for your money, basically. And that's much the same analogy you can use with new technology in oil and gas. So I've already mentioned the Appendix A, which we are going to start after we've done this intro to Part 2. Appendix A is about 100 pages, and it's an old compendium style stuff that's been done. So it talks about you have to have a platform or a floating vessel when you are producing stuff, but you don't really have to have that anymore. You can just send straight to land if you want to. So some of it is outdated, and I'm going to remark on it whenever we get to something that is a bit outdated in that part. But the main part, which is the subsea production system and the components of it, is more or less the same, so that we can still use it even though it's a bit outdated. We just have to just have to keep a critical eye on what might be old information, where we can have newer information instead. And that appendix mentions a lot of American standards, which they use. We, of course, follow Norwegian and European standards here in Norway. I'm not quite sure what Nigeria does, if they have their own standards for their oil industry, or if they follow international standards. We have some of the standards that have been developed here in Norway for use outside the Norwegian coast have more or less been adopted worldwide because they have figured that we have very few casualties at work. We have very few accidents and stuff, so we are fairly reliable operations when we're doing stuff. So I think the rest of the world is trying to sort of copy those results, not necessarily the way we do stuff specifically, but they want the same results as we have had here in Norway. Problem is now when they are pressed for prices with the oil price and everything, that's doing it the Norwegian way safely and everything means that we have had a huge focus on safety, and that's expensive. So that's one of the ways that the Norwegian industry can sort of tackle the low oil price, is to lower the focus on safety. So it depends if we're going to be more or less world leading in safety in a few years. We'll see how this crisis works out. Of course, a lot of the stuff with safety has been to many of the workers. It's a bit, you feel like a kindergarten child that's being held in your hand while you're working, because you have to do everything after procedures. Like if you're on a platform, you have to hold the rails when you're walking in a staircase. Just in case you slip with your feet, you are supposed to be able to hold on so that you don't fall down the entire staircase. And that's fair enough, because often the staircases on platforms, they are very narrow, the steps aren't all that deep, so you don't have all that much space for your foot when you're putting it down, and if you fall, you can actually risk falling over the side and into the water. So I see the point of having these kinds of stuff, but it's also been moved over to land, so that if you have, you can risk getting one of the bosses over at Kårstø, the startup plant. You can risk the bosses there if they see you walking down a staircase, wide, huge staircase inside an office building, and you're not holding the railing, then that's suddenly a problem. Oh, you have to hold the railing, because that's a part of the Statoil way of doing stuff safely. So some of it is unnecessary, but most of the safety aspect is very necessary. So we have the Norwegian law of petroleum industry. I've tried to translate these as well as I can. Sometimes I've been lucky, because when I've gone to the Norwegian webpage for it, there is actually an English version of it, so I've been able to use the official name of it. But some of the translations I've done are basically how I think they are supposed to be translated into English, because there are no official translations that I've been able to find. We have the general regulations from the Norwegian Petroleum Directorate. We also have something that's called the NORSOK standards, and that comes from, we have, was there a question? Or no? We have outside the Norwegian coast, we have something that is called the Norwegian continental shelf. And in Norwegian, that's written norsk sokkel. So we have nord sok, and that's the standards that are to be followed when you are working in the oil fields outside of Norway. And those are the standards that have been more or less adopted in many places of the world. So not the specific not the specific regulations inside of Statoil and stuff, but these NORSOK standards, which have been created by, now they're called standard.no. Earlier they were something like I think it was something like the Union for Standardization in Norway or something like that. And that was, they are a non-profit organization, so they make their livelihoods by selling these standards on their webpage, and other standards too. So they license American standards and stuff, and they sell them. And that's how they pay their the people that work for them. But basically, what they do is try to create. What they did with the NORSOK standards was that they took a lot of the different standards that were being used, and they merged the parts that they meant had to be used in the Norwegian part of the industry into one. And it's been proved to be a very fair standard to use. You don't end up doing loads of hugely expensive stuff for almost no gain. You end up with having fair design requirements for the stuff you're doing, so you don't have to make something much more complicated than it has to be when you're following these. And often what they do is they actually go when you go into cathodic protection. If we look at cathodic protection parts in NORSOK, it will actually more or less just recommend you to DNV, DNV GL as it's now called, which is DNV was the Norwegian Veritas. So but they merged, I think it was a year and a half or two ago, they merged with Germanischer Lloyd. Two L's. So they merged, so they became, instead of just DNV and GL separately, they became DNV GL. So they became one company. And what NORSOK does actually is it just tells you for cathodic protection, just follow DNV GL. Just do exactly what they recommend in their practices. And then they have a few extra informations that they add to the DNV-GL one, where they sort of say that, so, well, when you get into the Barents Sea where it's really cold and stuff, then the tables that the DNV-GL stuff use aren't the tables for temperatures and seawater contents and stuff. They're not quite right, so then they have just an amendment to that. So it depends a bit on where you are in the ocean, how stuff works. Yeah. When we are talking about subsea production systems, there are a few specific ones we can look at. So the U001 standard is directly for subsea production systems. And it also refers a bit to ISO, API, and ASME. So ISO is the International Standardization Organization, which is a mouthful. And API is the American Petroleum Industry. ASME. That's a bit more difficult to see. This one is fairly easy. International Standardization Organization, American Petroleum Institute. Fair enough. But this one, can anyone guess what it is? It's the American Society for Mechanical Engineers. It's a really heavy name there. But they actually have quite a lot of standards that they've created. So they've gone a bit further than what the societies in Norway and Europe generally do. the societies for technologists and engineers, or technicians and engineers in Norway, basically only acts as a union. So they're a union for the engineer workers. While in America they've taken it a few steps further, where they're actually creating standards and recommended practices and guidelines to use while they're working. So they are sort of taking on more roles than just being a union for the workers. We also have NORSOC U009, which is life extension for subsea systems. So it handles a lot of the stuff with, if we already have a subsea system, how can we extend the life of it? Because usually when they develop a field, they say that, well, we reckon that within 25 years we'll have gotten all of the oil out that we are able to get out of this field. But then 15 years later, new technology shows that, well, we can get 30% more of the oil out of this field, which means that it has to work for a longer time. After 25 years, it's still not done. So then they have to upgrade it and do certain modifications in order to extend the life of the system before they shut it down. You also have NORSOC L004, just piping fabrication, installation, flushing, and testing, which is handling quite a lot. So both handling how the pipes are to be fabricated, how they are to be installed, how they are to be flushed before you can send any oil or gas through it, and also how they are to be tested before you are to send it through. I've already talked a bit about DNV-GL. They have a lot of standards, and they also have a lot of recommended practices. And the standards are, if you are required to design something according to a standard, you have to do exactly what the standard says you have to do. But if you are also, if you're said to do it according to a recommended practice, you don't necessarily have to do it exactly as it says in the recommended practice, because it's only recommended that you do it this way. So if you have good arguments for, let us say you have a safety factor in the recommended practice, it says you should have a safety factor of 2, so that all of the loads that you're getting on your structure, you should multiply them with 2 when you're doing your design, just so that you are sure that everything is going to go well. If you have very good reasons for using 1.8 instead, you can give your arguments for it, that I will be using 1.8 instead because of these reasons, and then then it's basically up to your customer to decide is this okay. Are we going to let them use 1.8 instead of 2 as a safety factor? They have good reasons for doing it. And then maybe if you go from 1.8, or if you go above 1.8, you have to change the material so that you're going from steel to titanium. It's going to be hugely expensive to raise the safety factor from 1.8 to 2. So that might be a reason that the customer is like, well, we're going to half the cost of it if we go for 1.8 instead. So then the customer will most likely give the okay for doing that. However, if you go for the standards, if you have to design it from a standard, then the customer might actually say that, well, a representative from DNV-GL are going to have a revision on your design afterwards. But then you have to follow the standard exactly, because the guys from DNV-GL, they don't mess around. If they find the tiniest flaw, tiniest deviation from their standard, then they're, well, you have to do this over again. There's no mercy in them when it comes to that. But if a DNV-GL guy comes and looks at something that you've designed from a recommended practice, he will most likely be very, very easy to talk with. You just talk with him, you'll explain your case, and he'll most likely say, fair enough. So it depends a lot on exactly the situation that you're in. But that's actually how DNV gets most of their money. It's through direct projects and sending their representatives to check stuff. So that most of their standards and recommended practices, they are actually available for free on their webpage. So you can just go in and download it, which is great. So it used to be that with the no-stock standards also, but now I see that many of them, at least the largest of them, the most used ones, they are now, you have to pay for them in order to get them. Which is a bit sad. I think that was also one of the reasons why they were adopted all over the world, was that they were free of use. So DNV has a couple of specific ones that goes for production systems, which is the submarine pipeline systems one. And they actually have a system here for their naming. I'm not quite sure what the F is for here, but the OS is an operational standard. If it was a recommended practice, it would say RP instead. So that you can very easily, just by looking at the code designation of their standard, you can easily see if it's a standard or if it's a recommended practice. They also have dynamic risers. A riser is the pipe that goes from the subsea system down on the ocean floor and up to the platform or a vessel that is processing it. One thing that is very important when we are using laws and regulations, it's always to use the newest revision of it. Because if you are using a standard from DNV, if you're using this one, and the one you're using was revised in 2006, and you've done your entire design there, and then a guy from DNV comes, or a woman for that matter, a representative at least from DNV comes to look at what you've done, to revise it, and then he said, well, you used the 2006 version. There's a version from 2009. Why didn't you use that one? There's a whole lot of changes in it. So then you sort of end up getting, if you're lucky, those changes had nothing to do with your design, so that you're safe. It didn't, but you still have to go through it piece by piece and just check that everything is the same in everything that you've used of the 2006 version is still the same in the 2009 version. So it's very important to always use the newest version when you're using them, which is also part of the reason I think why universities and university colleges don't really use standards directly in their education. Because it would have been great if we could have just said that, well, here we have the entire NORSOC standard, we're going to learn this one. But the problem is if there's a revision on it, then you have to scrap the entire course and do it all over again the next year. So it doesn't really work that well. You can get courses and stuff from both from the standard.no guys and from DNVGL. They actually hold courses for the newest versions of their stuff. So you can do courses outside of school for that stuff, or after you've started work for that matter, if you want to update yourself. We're going to look at a couple of examples of recent systems. Those are the appendixes after A. I think they are B and C, or is it just B? I can't quite remember right now. Just appendix B, it says here. We are going to look at the Åsgard field, which is outside of Trondheim in Norway there. And we're going to look at the Ormen Lange field, which is, you see Åsgard, it's a bit further north than Ormen Lange. The difference is that Åsgard, they have an FPSO, a floating production, storage and offloading vessel. While Ormen Lange, you can see all of these guys, they're standing ashore. So Ormen Lange is sending everything all the way from out here in subsea wells, and they're sending it into shore instead. So everything out on Ormen Lange is subsea. There's nothing that's floating around out there. So that's a pretty cool field to look at. Too far. We also are going to look at some equipment that's been used both in Åsgard and in Ormen Lange. We're going to look at FMC Kongsberg. They have a system that is called HOST, which is basically how they connect their pipelines to the facilities. No, that's the other one. The HOST system is how they install everything through a moon pool on the rig. A moon pool, for those who are wondering. So if we have try to do a 3D sketch here of a vessel. So if we have a vessel that's out working and they're installing stuff, usually they install it over the side. So they have cranes that lift it over the side and everything. But then you have a lot of waves here that the waves will smack whatever it is you're lowering down. So if you ever jumped into a pool or anything and landed flat on your belly, that hurts. It's the same for the equipment, and there's a lot of force that hits the equipment when you get that stuff. So one way around it is to use a moon pool, which is actually a shaft that goes down through the middle of the ship. So it goes down all the way to the bottom of the ship. Inside there, and then you can lower everything down through the shaft instead. Because the water inside there won't be any waves in that water, because it will be kept still by the sides of the ship. So that's a good way of doing it, but it sets a lot of requirements to the size of the ship. You have to have a certain width and length of the ship in order to get this. You have to have space for everything that you're going to lower down. So those are really expensive ships to use. And we have an Appendix C. We're going to look at an ROV tool, which was used to pull in the pipeline. So basically, when we were down at the seafloor, you have the structure, the subsea structure, and everything, and you have a pipeline that's placed here. And it's pretty difficult to connect this. So what they've done is that they've created a system that sort of just pulls the pipeline in and then connects it. So it's a winching system operated by ROVs and stuff. So it's really cool to see how they solve stuff. So it can actually pull with a force equal to 20 tons. So that's pretty heavy. So then we have development trends. We're seeing that only wet systems are being used. And a wet system just means that everything that is down on the ocean floor is in contact with the seawater. So what they used in the beginning often was that they used sort of a shell that was in contact with the water. So they would have create sort of a shell here, which would be in contact with water. The water would be around here. And then you can have all of the equipment inside. So all of your equipment was inside there, whether it was valves or whatever it was, that was in there, and it was dry. So you could actually send people down there, and they would keep it at 1 atmosphere in there, so that you didn't need a diver to send down there. You could actually lower down sort of looked a lot like a diving bell. You would connect it here, and you would have a worker that would go in here and fix whatever it was. They've gone away from that, so now they only use wet system. It has a lot to do with the depths and the pressures. If they're going to maintain this, it has to be really strong, at least down at 3,000 meters. And What are you going to do if you send a person down here and something happens down at 3,000 meters? You're completely screwed, that person. So it's better to use an ROV where you get some equipment that's destroyed, but that's everything. So we're going over to more and more diverless systems. There's still a lot of divers in use, but mostly usually it's not on new developments. They are usually working on old fields, so they are doing maintenance work and replacements, and maybe even upgrades if they are extending the life of a field. So, but those are areas where there have always been divers. So those were created for divers to work at. And sometimes the older equipment that subsea is really not designed for an ROV robotic arm to use it. It's designed for fingers to use, so that it's difficult for an ROV to just take over the tasks of a diver there. But more and more divers are mostly being used inshore. So close to the shore, they are always being used for bridges, docking areas and stuff. So that's mainly where divers are being used now. We're seeing horizontal Christmas trees. Many of you are probably wondering, what am I talking about? A Christmas tree? That's basically just the valves that are coming up. You have the well. You have the well going down into the reservoir, and then you have a lot of equipment there to connect the well and keep it safe. And then you have a tree with a lot of valves here. So it's called a Christmas tree because it was often placed a bit like this. So it's basically exactly the same as they have on onshore oil rigs. So if you go to Saudi Arabia or something, that's what you're going to see everywhere when you drive along the oil rigs there. And that was also what they did in the dry systems. They would have these the same kind of Christmas trees as they use on land. They would use those down below the surface because they had them in that dry area, so they could use them there. But now they've developed them in different materials and different designs so that they can use them while they are wet. And now they are going more and more over to some of them that are called horizontal, so it's just a different design for them. We'll get closer into that in Appendix A. Through flow line methods are less used, which means that it's actually connected to the switch to horizontal Christmas trees. Because what they did here in these Christmas trees, if they are going to fix something inside there, inside the well, then they would actually pump equipment down through the same pipes that send the oil up. They would pump the equipment down, and then they would send it in here. And then there was a lot of calculations on exactly how much pressure do we need to get to exactly there, and then it has to do this operation and everything. So it's fairly complicated stuff to do if you're going to fix something in there. It's a whole field in itself. You actually, if you want to work with that stuff, you usually study to become a subsea engineer and not a mechanical engineer. But it's being less and less used because when they're going over to the horizontal ones, they can actually lower down a wire from a vessel up top, and they can just slip it in through a valve at the top. So they can use a lifting wire instead of having to pump something through the oil pipes. And we are going over to more multiplex electro-hydraulic control systems. They are basically means that you have a lot more control of the stuff you're doing. We're going deeper into those when we are in Appendix A. It means that you are combining hydraulic and electric signals. So you are using hydraulics to perform actions, close valves, open valves, and everything like that. But you're using electric signals to tell the hydraulic system what to do. So all the way in the beginning, they had direct hydraulic control, which meant that they had a single hydraulic line going to every single component that was supposed to do something. So then you had to be up top and you had to just turn valves on the correct line in order to tell it to do something subsea. But with this electro stuff, you just need a control panel, and then you can do everything by just flipping switches instead. So, and it's a lot more responsive, and you also, this multiplex part means that you have built-in sensors and regulators so that you can actually get readings of what you're doing. Well, now I have a 60% flow through this valve, which means that it hasn't opened fully. So then you know that, oh, something's wrong with that valve. We have to do some maintenance on it. So that's a huge step forwards. We also have ROV-based intervention techniques, which is basically when something goes wrong, that's when you do interventions. So then you have to fix stuff, and you can do most of it by ROVs now. You have increasing degrees of standardization. I think that one is it's a bit far off still. There's still a lot of custom stuff being done everywhere. Especially like up until a few years ago when the oil prices were high and there was a real rush to do a lot of development at once. Then it was often easier to just say that, well, just do this. And the startup would just hand it over to another company, and that company would do their stuff. And then for another development, they would hand everything over to another company, and they would do their stuff, because the first company, they didn't have the capacity to do both at once. But that meant that this company and that company were basically designing solutions for the same problems, and they are designing different solutions. So it's a lot of work on top of work being done. So if we had a lot more of standardization inside that, so that if you could have used exactly the same equipment on every single well that you are drilling, that would save you a lot of money. So that's what they're working at achieving now. A lot of, especially now when they have a huge focus on saving money. They're trying to do a lot of this. We see more processing plant equipment placed on the seafloor. So Statoil have been huge on that, trying to get more and more of the stuff that normally is on top, on a rig or a floating vessel or ashore. They're trying to place more and more of that down here, down at the seafloor. And much of it is actually because down here you have the perfect conditions, because you have approximately 4 degrees Celsius temperature. It's constant. It's a perfect scenario for cooling stuff. If you have compressors that are working, compressors create a lot of heat, as you remember from thermodynamics. So having a 4-degree reservoir where you can just dump all of your heat into the 4-degree ocean water, that's perfect. If you're up top on a rig, you would have the atmosphere to deal with, and suddenly in summer you have a 25-degree day. You will have huge problems getting proper cooling for your stuff, which means that you have to have a lot more complex cooling equipment for it. So it's there's a lot of things that can be done easier down at the seafloor. Of course, they are also more difficult, because when you are creating something that you're placing down on the seafloor, where you basically can't send in a mechanic to fix stuff whenever something breaks, you have to make damn sure that it's going to not break. So it requires a lot of clever design, but still it's a lot cheaper in the long term to do this. So what they're trying to do is at least crude separation. Separate the flows if you have both gas and oil. Not fine separation where you're separating into different types of oil and everything, but just managing to separate the different components in the flow. Multi-phase pumps. That is, if you haven't separated it, you have a multi-phase. You have both gas and liquid oil in it. Compressors, use those because of course you have one of the ways that they are extending the lives of fields is that they pump in. They have a different well over here, where they actually pump in something to the reservoir. So whether it is seawater or if it's some excess oil or something. So what they do is that they pump it in here, so they sort of try to maintain the pressure inside the oil field so that the oil field will keep pushing the oil out of the original well. So if they can put the compressor there, that's very good. The same with huge electrical motors to do stuff for all of this. As I mentioned with the cooling stuff, it's a great place to have it. Sensors and control systems are very good because then you can get information exactly where you need it. You don't have to wait until the oil reaches the platform before you can get the information. So it's very good to have those down there. Yeah, and a lot of this requires development of new installation and maintenance methods, basically like installing these compressors and stuff that can be huge, the size of houses and stuff, and you might need to create new methods of lowering them down because they are basically larger and heavier than anything else you've done before. So, and as we get deeper and deeper, what they use before it gets too deep is that they use guidelines, which is basically just wires that they connect to the frame at the subsea floor, at the seafloor. Because then they can lower something that is also connected to these wires, so it will follow the wires all the way down, and then it will just be placed exactly where it's supposed to be placed. But when you get deeper and deeper, if you get down to 3,000 meters and further, these wires will start to bend, so they will, instead of being fairly straight, you will start to have large curves on them and stuff, and it's starting to be a lot of weight and a lot of different complications in using it. So they are using more and more guide wireless systems when they are setting things down, which means that they're just lowering it down on lifting wires, and then they are, instead of guiding it all the way down, they start guiding it when it is fairly close to the structure. Basically using large funnels and stuff where you can get sort of parts of the new module that is coming down. It has some, call it, you place a huge funnel on different locations, and the module that is coming down, it might have some sort of guiding tip here, which will hit the funnel, and then it will be slowly guided down and into place where it's supposed to be. The funnels are really huge, so that they have a lot of leeway when they're lowering it down. Yeah, that was it. Then we are going to start on Appendix A next week. So if you just take a little look at it now before we do a break, you will see that the first part is a table of contents. We're going to skip that one. After the table of contents, there's a glossary. And the glossary is just a little description of several industry-used terms that the appendix uses. So it can be smart if you're reading through it or in the lectures and saying stuff and you say, what does annulus mean? And you can go into the glossary and you can look for the word and see if you can get an explanation for it. There's also a list of applicable standards, and then we get into the appendix itself. One thing that I want you to think about before the next lecture is that all of the figures that this text refers to, they are all the way at the back of the appendix. So it might actually be wise to just open your folder, pull all of the figures out, and then as we go along here and it says see figure 1.1, then you can just say, there's figure 1.1, and you can maybe place it on the page behind there, so that you get a more logical placement on your figures, so that they follow the text instead of all of the figures being all the way at the end. I will be showing the figures up here also, but still it's nice when you are reading for your exam and stuff at the end of the term. It will be nice to actually have the figures close by so that you don't have to constantly flip the pages to see all the way at the end there. So, and that's just because this part of the compendium, that's just a PDF that we got. So it's not something I have translated exactly this part. So, but if it had been something I had translated, I would have fixed the figures into the correct positions. Because I hate that stuff when it's not correct. So we'll do a break and then we'll start the CAD stuff afterwards.